Okay, Raiders, let's take a look at another law of conservation of momentum scenario here in our distance learning for Unit 1. So now we have a situation here where we have a railroad car of mass 5,000 kilograms. It's moving 8 meters per second, and it collides with a stationary railroad car of mass 7,000 kilograms. After the collision, so we have a kind of a before and after situation. After the collision, they stick together and move down the track together. At what speed do they move down the track? Well, again, we can use our law of conservation of momentum concepts to analyze this. And you notice, like in the last problem, I just cut and pasted some pictures from online because in my last video when I drew a car, I didn't want people making fun of me and I felt insecure. So here we go. So unless you got a problem with Google Images, this should be good to go. So we know the momentum before the collision is going to equal the momentum after the collision, according to the law of conservation of momentum, assuming there's no outside factors, which in reality there would be, but we're simplifying this a bit. So generically, we can call this railroad car A, railroad car B. So the momentum of car A plus the momentum of car B before they collide, that represents the total momentum of your system before the collision. And that's got to equal P prime, again, the prime symbol just denotes the momentum's different after the collision, of collectively A plus B, because they stick together. So we'll break each of these down individually. So we have the mass of car A times the velocity of car A. That's the momentum of car A, plus the momentum of the mass of car B times the velocity of car B. This represents our total momentum before the collision. So we can substitute our values in. Railroad car A has a mass of 5,000 kilograms and it's going 8 meters per second. And railroad car B, which is bigger, is 7,000 kilograms, but has a velocity of 0. So if you break this down individually, car A is providing 40,000 kilogram meters per second of momentum, but car B, because it's stationary, is not providing any momentum. So the total momentum of our system before the collision is 40,000 kilogram meters per second of momentum. That's the exact same amount we have to have after the collision, no more, no less. So P prime of the bumper cars, the railroad cars after they stick together, their momentum after the collision is going to be the mass of A plus B, the two cars together, multiplied by V prime of A plus B. So collectively, when they stick together, the 5,000 and 7,000 kilogram separate cars now become one 12,000 kilogram car going at some new velocity. So divide both sides by 12,000. And what you end up with is V prime, or velocity after the collision, of about 3.33 meters per second. So let's reflect and think about why this should make sense. So first things first, everything's moving towards the right. So if we initially made the velocity towards the right for a railroad car a positive, then as they move off together in the same direction, it should also be a positive velocity. And note the quantity. Notice that this is a little less than half of the original 8 meters per second. When the two cars collide, the stationary car was heavier than the first one. So basically all the momentum provided by car A is now responsible for moving car A and B, but the mass is more than doubled. So the velocity now is less than half of what it was. So hopefully this makes sense. And as always, as we're moving forward here, if you have any questions, contact me on the Remind app, or you can send me questions directly from OdysseyWare when you're on a particular problem that's giving you difficulty. Raider Nation.